In this lesson video, we're going to be learning about section 4.6, completing the square. Our objectives are that we can solve equations by completing the square as well as rewriting functions by using the same method. So we are going to solve equations that contain perfect squares by finding square roots. The simplest form of this case would be ax squared equals c. So there's no b value involved, and you can see in the first example in part A and B there is no b term, there's no bx at all. So we're going to take a look at part A. It's 4x squared plus 10 equals 46. What we want to do is isolate the variable term. So first thing we want to do is subtract 10 to move it over the other side. And we have 4x squared equals 36. Divide both sides by 4, and we get x squared equals 9. And it's the best situation when the other side is equal to a perfect square, when we have something squared. And 9 is a perfect square. So when we take the square root of 9, you need to make sure you put a plus or a minus in front of the square root of 9, because remember, when you plug in a positive or a negative into something squared, you can still get out a positive. So we want to account for that positive and negative sign possibility. So we get x equals positive or negative 3. So that means the solutions to this quadratic are positive 3 and negative 3. And that's what that plus or minus symbol means, positive 3 or negative 3. Part B is very similar. We want to add 5 to the other side. So we get 3x squared equals 30. Divide both sides by 3, and we get x squared equals 10. So in this situation, we do not have a perfect square on the right side. So when we take the square root of both sides, we're not going to get a nice answer. We're actually going to get an answer with a radical in it. So we get x equals positive or negative square root of 10. We cannot reduce square root of 10 because there are no perfect square factors of 10. So that is our final answer. In example 2, we have a real-life application problem involving architecture. It says, while designing a house, an architect used windows like the one shown here. What are the dimensions of the window if it has 2,766 square inches of glass? You may have noticed that the window actually contains two different shapes. We have a rectangular part and we have a semicircular part. So let's find the area of each. Well, the area of a rectangle is the formula A equals length times width. So we know the length and the width. They are given to us in the picture. So we need to multiply 2x times x. And that gives us 2x squared. For the area of a circle, it is pi r squared, but a semicircle is only half of that. So we want 1/2 times pi r squared. Now take a look at this semicircle. We know that the diameter is x, so that means the radius must be 1/2 of x, because remember from geometry, the radius is 1/2 of the diameter. So we want to substitute in for the radius 1/2 x or x over 2, which is the same thing. And when we multiply that and reduce, we get pi over 8x squared. So now we have the areas of the two different pieces of the window. So that means the total amount of glass used is going to be set equal to the total area. So we're adding the two different pieces. The area of the rectangular part is 2x squared, and the area of the semicircular part is pi over 8x squared. So we're going to be adding those two terms together and setting them equal to the total amount of glass, and we were told that in the beginning, 2,766 square inches. So now what we need to do is solve for x to figure out the dimensions. Hopefully you notice that both terms had an x squared in it, so that means that's the GCF. So I'm going to be factoring out the GCF, which is x squared, and putting it behind. We've mostly put it in front, but the order or the location of the GCF doesn't technically matter. So in this case, I'm going to put it behind. So that means in parentheses we have 2 plus pi over 8. And now we have our equation in the ax squared equals c form that we've been working with earlier. So we want to obviously isolate the x value. So we want to divide both sides by 2 plus pi over 8. Now we have x squared equals 2,766 over 2 plus pi over 8. And we want to take the square root of both sides. to get the x by itself. So now I'm going to show you how to type that in your calculator. All right, so let's go to our square root function, which is second x squared. There's a square root, 2,766, and then open up another set of parentheses, divided by, and then open parentheses, 2 plus pi is located behind the caret symbol, so second pi divided by 8, and then close parentheses twice, and press enter. So we're getting an x value of approximately 34. Now, of course, we have the plus or minus symbol in front, as always, when we divide or actually take the square root, but length cannot be negative. So that means the rectangular portion of the window is 34 inches wide by 68 inches long. And the way that I got that 68 inches was I just doubled it, and I'm using the dimensions that were given. Now that we know the dimensions of the rectangular portion of the window, we can easily find the dimension or the radius of the semicircular portion. So since we know the width of the window is 34 inches and the length is 68 inches, we can find the radius just by dividing the width by 2, because as we talked about before, it's just 1/2 of that x value. So half of 34, or 34 divided by 2, is equal to 17. So the radius is 17 inches. So we found out all the dimensions of this window, and we use the process of taking square roots and reducing to do so. Sometimes we're given a perfect square trinomial that is equal to a constant. If we are in this situation, we need to factor the perfect square trinomial into the square of a binomial and then find the square roots. So we're going to be using this process in example 3. So we're given the quadratic equation x squared plus 4x plus 4 is equal to 25. So you have noticed that this is a perfect square trinomial. So remember, for perfect square trinomials, you can take the square root of the first number and the last number and square that sum. So we have x plus 2 squared. Now, if you are still struggling with perfect square trinomials, you can still use the x method, taking the last number and the middle number, and the numbers that work are 2 and 2. So since we have the same number twice, that's why we're squaring that sum, x plus 2, and we're setting it equal to 25. From there, we can take the square root of both sides to get rid of that 2 in the exponent. Remember to put a plus or a minus in front of the square root of 25. That cancels out the square root and the exponent of 2 on the left side. So we just have x plus 2 is equal to plus or minus square root of 25. That is equal to positive or negative 5. And then to get x by itself or isolated, you want to subtract 2 to the other side. So we have x equals negative 2 plus or minus 5. So we do want to get the solutions from there. So that means we either have x equals negative 2 plus 5, which is equal to positive 3, or x is equal to negative 2 minus 5, which is equal to negative 7. So our two solutions for the given quadratic are positive 3 and negative 7. Sometimes we're given quadratics that are not perfect square trinomials. In this situation, we want to use the completing the square method that will allow us to factor the completed trinomial as the square of a binomial. So in this form, we have the a, or the leading coefficient, as positive 1, and we have x squared plus bx. If it's not a perfect square trinomial, we're going to be using the coefficient b to find a constant so that the new trinomial is a perfect square, and then we can just factor it as the square of a binomial. So this is visually what the completing the square process looks like. So you can see right here that we just have a rectangle. Dimensions are x and x plus b. And if we multiplied that, we would get x squared plus bx, which is essentially the area. What we're doing in this middle picture right here is we're dividing that b portion, that yellowish orange portion, into 2 equal pieces. So that's why it's b over 2, or b, or 1/2 b. And then when we do that, we have this missing piece in the top right corner. So the completing the square process allows us to make a perfect square, literally a perfect square, such that when we multiply the two dimensions, we get a perfect square trinomial. So here is the key concept box. You definitely want to have this down. So we can form a perfect square trinomial from x squared plus bx by adding b over 2 squared. So there's a little jingle that I found when I was researching how to make this process the easiest. I found this little jingle and I write it down for you and explain it in a second. I just want to reiterate what I was talking about a moment ago. The a value needs to be equal to 1 before you complete the square. So if the a value is not equal to 1, we will need to factor that out before doing anything else. So here's a little jingle, and I know it doesn't rhyme, but it's something to help you remember this. So what you want to do is take the b, whatever number is in the b position, which is the number in front of the x, take that number, half it, which means divide by 2, square it, which means raise it to the second power, and add it to both sides. So it's take the b, half it, square it, and add it to both sides. So I'll show you what I mean in example 4. It says, what value completes the square for x squared minus 10x? Justify your answer. So what we want to do is just put a little b below the negative 10. That's our b value. So we want to take the b, half it, and square it. And since we don't have an actual equation, we don't need to add it to the other side, but if we did, then we would do that as well. So negative 10 over 2, half it and square it. The number inside is a negative 5. Negative 5 squared is 25. So now we want to put that in the C spot. So take the b, half it, square it. So now we have x squared minus 10x plus 25. That is now a perfect square trinomial, so that means we can factor it into the square of a binomial. So we can write x minus 5 squared. So that would be the factored form of the perfect square trinomial that we just created. And one more time, using the x method just to prove that this works, 25 on top, negative 10 on bottom, negative 5 times itself does give you positive 25, and it does give you, when you multiply, and then when you add, you get negative 10. So one more thing I want to show you is that this negative 5 right here is actually the same number that we squared, and that will always be the case. So if you want to remember that shortcut, feel free. So the square of this term would be x minus 5 squared. So that's the factored form of the perfect square trinomial. In this key concept box, we have a really nice summary of the process of how to solve an equation by completing the square. So feel free to pause here to jot down these 5 steps. So step 1 is we need to rewrite the equation in the form x squared plus bx equals c. To do this, we want to get all terms with the variable on one side of the equation and the constant on the other. The constant is the c value. And then we want to divide all the terms of the equation by the coefficient of x squared if it is not 1. And I briefly mentioned this earlier, that a needs to be 1 before you complete the square. Step 2, complete the square by adding b over 2 squared to each side of the equation. So that's a little jingle. Take the b, half it, square it, and add to both sides. Step 3, factor the trinomial. Step 4, find the square roots, and lastly, solve for x. So let's follow this process in example 5. In example 5, we're given the quadratic 3x squared minus 12x plus 6 equals 0. First thing we want to do is move over this c value of positive 6 by subtracting 6 from both sides. We always want to make sure that the c value is blank before doing anything else. So we get 3x squared minus 12x, leave a little blank space, equals negative 6. From there, I noticed that the leading coefficient a is not 1, so what we want to do is divide everything by that number to make sure that that is 1. So divide everything by 3, including the other side. So now we have x squared minus 4x equals negative 2. So now we have the perfect conditions for completing the square. So the b value in this case is negative 4. So I'm going to do this on the side. Negative 4 divided by 2, take the b, half it, and square it. So the number inside is negative 2, and squared, that would be positive 4. So the number that we want to add to both sides is positive 4. So plus 4 plus 4. From there, we now have a perfect square trinomial on the left side. So we can factor this as x minus 2 squared. And you can always do the x on the side, the x method on the side, if that helps you. And you can see that we have negative 2 multiplied by itself. And one more thing, this negative 2 is the same as the one that we squared. So that's that shortcut I just talked about recently. And then on the right side, we have positive 2. We're actually pretty close to the answer now. We just factored, so we need to find the square roots and then solve for x. So we need to take the square root of both sides. Make sure you have a plus or minus on the right side. And now this 2 and the square root on the left side are canceling because they're the opposites of each other. So we have x minus 2 is equal to plus or minus square root of 2. Last step, add 2 to the other side. So that means our solutions are 2 plus or minus square root of 2. If we wanted to check our results, we could plug them in and replace the x in the original equation with both of our solutions. One common use of this completing the square method is to change a quadratic from standard form into vertex form. So you can see in example 6, we have the quadratic equation y equals x squared plus 4x minus 6. This is currently in standard form, and we need to change it into vertex form. And then from there, once we have it in vertex form, we need to name the vertex and the y-intercept. So like we did in the previous example, we want to get the C spot free. So we want to add 6 to the other side. So we're just relocating the 6 for a while. So we have y plus 6 is equal to x squared plus 4x. So you can see the C spot's ready to go. So we want to take the b value, which is 4, take the b, half it, and square it. And that is equal to positive 4. So we want to add 4 to both sides. So plus 4 plus 4. So now we have y plus 10 equals x squared plus 4x plus 4. And now it's a perfect square trinomial, so we can factor that as the square of a binomial. So that would be x plus 2 squared. From there, we just need to subtract the 10 to make sure that the y is by itself. So we have y equals x plus 2 squared minus 10. So this is in vertex form now. So hopefully remember that the benefit of vertex form is to easily find the vertex of the parabola. And I wrote down the general vertex form right below to remind you what it looks like. So remember the vertex form has HK as the vertex. So because we have a plus 2 in the parentheses, we're essentially subtracting a negative 2. So that means the x-coordinate of the vertex is negative 2, and the y-coordinate is just as it seems, k is equal to negative 10. So we have the vertex coordinate of negative 2 comma negative 10. The y-intercept is actually easily found in the standard form that we were given, the c value. So that means our y-intercept is at the coordinate 0, comma, negative 6. I would like to show you the quick checking process that you can do with your graphing calculator. So turn your graphing calculator on and go to y equals and replace any previous quadratic equation with the one that we're given in this example, x squared plus 4x minus 6. From there, let's go to the window, and I suggest changing your x-min, x-max, y-min, y-max to match mine. So I have negative 20 and positive 20. From there, we should be able to go to the trace feature and see our parabola there. And to find the minimum value, or the vertex, it is the minimum in this case since the parabola is opening up, we can go to second calc and then down to minimum. And then now you need to choose a point on the left side and a point on the right side of that vertex. And we find out that the minimum is at the approximate coordinate point of negative 2 comma negative 10, which confirms what vertex we got when we did it together. Now for the y-intercept, it can easily be found by looking at the table. So go to second table. If your x values are still going up by 0.1 from a previous example, you want to go to second table set and change the change in table to positive 1, and you can change this table start to any integer value. So let's go back to the table, second table, and then now let's look for the y-intercept. So when x is equal to 0, what is the y value? So we see right here x is equal to 0 and the y value is negative 6, so that also confirms our y-intercept that we found together. Here are our lesson check problems for lesson 4.6, completing the square. Take a moment, you can pause here and write down the lesson check problems, make sure you show your work, and let me know if you have any questions next time we see each other.